Hi, and welcome to Codex. Our speaker today is Amit Singer, who is professor of mathematics at Princeton. Professor Singer received his PhD in applied mathematics from Tel Aviv University in 2005 and served as a Gibbs assistant professor in applied mathematics at Yale before joining the faculty at Princeton in 2008. Amit has established himself as a leader in the mathematical analysis of noisy data provided by cryo-electron microscopy. Today, he will tell us about the method of moments. Take it away, Amit.
Okay, thank you very much, Emily, and all the organizers for inviting me to give a talk today in your Zoom seminar. Indeed, I will talk about the method of moments in cryo-EM. And like I told the organizer, this talk is mostly going to be an overview rather than focus on one particular paper. And I'll try to make the case of why cryo-EM is such a fascinating field for mathematicians and others to explore, especially today, and some of the challenges that computational mathematical challenges that we're facing. And for those of you who are new to cryo-EM and don't know much about it, I put here three review papers targeted at three different audiences, but biomedical data science, engineers, and mathematicians. So, and this can give you a door to the to enter the field. So feel free after the talk to look at any of those. These are with my collaborators, Fred Sigurus, Tamir Ben-Dori, Alberto Bartisaghi. So whatever field you identify most with, this can be useful for you. So what is cryo-EM, or more specifically single particle cryo-EM? This is a method for determining three-dimensional structures of biological macromolecules. And nowadays it's very fine resolution, even atomic scale resolution. We'll get to it soon. And the way it works is that, unlike the classical method of X-ray crystallography, it does not require crystallization of the molecules at all. Instead, all the practitioner needs to do is to flash freeze molecules in a very thin layer of ice, and then shoot an electron beam using the electron microscope perpendicular to the specimen. And then what you obtain are, by the way, can you see that the virtual hand when I'm moving it?
Yes.
Okay, great. So what you obtain are images, that tomographic projection images called micrographs, and those micrographs contain projections of individual particles, of individual molecules. Here what you see is just an artist's concept. These are not real molecules. They were generated on a computer. And here is just an instance of this artificial micrograph. Usually the first step is just to pick particles. Okay, this image segmentation problem where you just find the location of the particles and segment them out of the large micrograph. Now, as you can see, we obtain images of molecules at arbitrary orientations, and we do not know these rotations ahead of time. So every molecule here is arbitrarily located. Okay, we also don't know the location, and also arbitrarily oriented in a free space. And because at the moment of freezing, just every molecule just picks some random location and orientation. And on top of that, there is an issue of very high level of noise due to radiation damage. So as the electron beam goes through the molecules, it basically breaks down the chemical bonds that make the molecule. So there is a maximum dose allowed if you really want to get fine details of the molecule. And this renders the images to be very noisy, and I'll show you real images on the next slide. So the standard cryo-EM reconstruction problem is how to go from multiple tomographic images that look like this and to predict the 3D structure. So here is, just to give you an idea of how experimental images look like. On top you have, you see two projection images, particle images, out of a much larger sample of about 17,000 images. And I hope that you can appreciate that the images are quite noisy, and it's very difficult to even see the molecule here. You need to have a very trained eye to convince them that there is a molecule here. Here is a different data set from a different collaborator, Adam Frost at UCSF, of a much larger data set of almost 100,000 images, also much larger images. So it's amazing that from images like that, one can actually find a 3D structure, okay, at high resolution. I'm not showing you the 3D structures here, but okay, that led to papers in high-profile journals. Now you can think about this problem for those who, as kids, like to solve jigsaw puzzles, as a three-dimensional puzzle, where every piece of the puzzle corresponds to a projection image, and the location of the piece on the globe is associated with the viewing direction, okay, at which we would look at the molecule. So every such projection image gives us some information about the molecule, and we don't know the orientation of the molecule, so we somehow need to put the pieces of the puzzle together in a mathematical consistent way, and also overcoming the very high level of noise in the images. And so this is a useful way to think about cryo-EM, and later on I'll show that it's actually the wrong way to think about cryo-EM. Okay, there are ways to solve the 3D structure even without estimating the location of the pieces of the puzzle. Okay, but this will come soon. Okay, so if we want to solve a jigsaw puzzle, we need to find a way to put pieces of the puzzle together. Okay, so if I'm showing you two images, what's the relationship between them that would allow you to locate them on the globe? So there is a very simple and beautiful theorem in computational tomography called the Fourier projection slice theorem. And what it says that if you take your 3D molecule and then look at 2D projection images, 2D tomographic projection images of the 3D molecule, and then you consider the 2D Fourier transform of the 2D projection images, then those 2D Fourier transforms correspond to the restriction of the 3D Fourier transform of the molecule to central slices. Okay, so these are slices that go through the origin in K space or in the reciprocal space, and whose orientation is just determined by the orientation of the molecule. So again, if you look at the 2D projection image and take its Fourier transform, then you can populate the 3D Fourier transform with the values of the 2D Fourier transform. So if you knew the orientations, the unknown orientation of the molecules, then you can simply populate the entire Fourier space with your Fourier transform samples, and then do Fourier inversion and get the molecule back. The point in cryo-EM is that we don't know the orientation. So we know that we somehow get noisy slices, but we have no idea how to insert them in a consistent way. Okay, so I'll get soon to how to actually solve the cryo-EM problem. And now I want to give you a sense of what's going on in the world of cryo-EM. Okay, if whether or not you are a mathematician or not. Okay, so there's been like a tremendous advancement in the technology. Okay, so if in the old days you would get very low resolution and structures that would look like blobs, nowadays, okay, so this picture is basically moving from left to right, and this could be like the axis of time, but it's actually just one molecule called the beta gal. On the right, you see that like in 2015, people already got like 2 angstrom resolution, okay, like near atomic scale resolution. And this advancement is mostly due to new detectors that can now actually take, instead of single images, but actually can take videos, and we can do motion correction, and the thing that I don't want to get into in this talk today. But and the other aspect is that of new image processing and data analysis algorithms. So due to those couple advances, both in hardware and software, if you wish, hardware and algorithms, we can now get to much better resolution. And people in the field refer to this as the resolution revolution. And in 2017, the Nobel Prize in chemistry was awarded to 3 of the pioneers of cryo-EM. As you can see from the citation, for the development of cryo-EM, which both simplifies and improves the imaging of biomolecules, this method has moved biochemistry into a new era. And this was not new, okay? So in 2015, Nature Methods selected the cryo-EM as method of the year 2015. And this is another paper from Science around the time. It's in 2014, the resolution revolution. And here in green, you see what I told you a minute ago, advances in detector technology and image processing are using high resolution electron cryo-microscopy structure of biomolecules. This is perhaps more recent, okay, so to show you, again, it's from 2020. It shows you 2 interesting figures. One is the number of structures that are deposited, okay, by structural biologists. And you can see the exponential growth of cryo-EM, okay, just the number of structures that have been determined by cryo-EM compared to the number of structures by X-ray crystallography, which is still considerably larger, but you can see that the trends are not predicting a bright future for X-ray crystallography compared to cryo-EM. And I'm sure that if we more data from 2020, 2021, then the trends continue. And also, if you look at the resolution, okay, so that's the average, in red, you see the average resolution obtained by cryo-EM structures. Okay, so it hovers around, I don't know, like 15 angstrom resolution, which is not very good. And then you can see the resolution revolution, okay, how the resolution improves, say after 2013, 2014. And this trend continues, and that's like the best resolutions of structures that have been deposited. So early in the pandemic, okay, so you see this is a paper in Science from March 2020. It actually appeared on the bioRxiv in February 2020. So this is March 2020. This is exactly 1 month before I was admitted to the hospital because of COVID. So you see that the spike protein of the coronavirus was structured using cryo-EM, and this is of course has a lot of importance for at the time for vaccine development, as you can also see in the abstract of this paper. This paper, for example, has already, I think, nearly 7,000 citations. Okay, it appeared just 2 years ago. Okay, okay, so December 2020. Okay, so again, Nature selected like the 10 most remarkable discoveries of 2020. Obviously, viruses led the way in 2020, but also you see microscopy. And the reason why microscopy is here is because that year cryo-EM was able to reach atomic resolution. So not just near atomic scale resolution, as I mentioned before, like 2.2 angstrom, but here you see a 1.2 angstrom reconstruction of a certain molecule. And so there are 2 papers in Nature that year that actually broke that barrier. Moving now to to even more recently. Okay, so this is a method of the year 2021 of Nature Methods. This is not for cryo-EM, but still protein structure prediction. So I believe many of you heard of AlphaFold, or if you didn't, it's really an interesting thing to look at. So these are basically deep learning-based methods for predicting 3D structures of proteins and protein complexes by training on many structures that have been determined using X-ray crystallography, cryo-EM, NMR, and so on. So protein structure prediction is still very interesting, and even in that, even when they selected the AlphaFold as method of the year, in the methods to watch, you can see basically the heterogeneity problem in cryo-EM, or what is called the dynamic direction for cryo-EM, was selected as one of the methods to watch. So because cryo-EM is able to give you, the data consists of individual images of individual molecules. If those molecules actually have some structural variability, so molecules often come in different conformations. They do not have a static, rigid structure. So for example, I can see the molecule here that has two strands that can open and close. So you would like actually to reconstruct from the data the entire distribution of potential conformations or possible structures, and not just one average structure. And cryo-EM actually offers this ability to the heterogeneity problem, whereas other methods like X-ray crystallography and NMR would have much harder time because the measurements are superposition or aggregation of all the molecules in the sample or in the crystal. Okay, so I hope I was able to convince you that cryo-EM is a very interesting problem from the scientific point of view. In my group, we developed algorithm for a single particle reconstruction, and we have an open source package now in Python. We started with MATLAB, but in recent years we switched to Python. And for any of you who are interested in developing algorithms or to test some mathematical ideas on cryo-EM data, I would really encourage you to use Aspire. This would save you a lot of time of how to deal with cryo-EM data, and basically we've implemented a lot of tools that you would find useful. Okay, so let's see. Okay. So if you would ask me, Amit, what would you say are now like the important computational challenges and opportunities in cryo-EM? I would say that there are three interesting research questions. One is how to reconstruct small molecules. Okay, these are not really small molecules, but they're a lot smaller than what cryo-EM is now capable of. So I'll show that cryo-EM right now is a limit size or size limitation, that small molecules cannot be easily reconstructed or not at all. There are many interesting open problems related to the heterogeneity analysis, okay? And these are like what I told you about different conformations and reconstructing the manifold of conformations. And there are also very interesting questions about how to integrate cryo-EM and AlphaFold. Okay, so AlphaFold can give you like really good priors on how the molecule should look like, and so how to integrate that with cryo-EM. Today, I'll not be able to talk about all three topics, so I'll just focus on the reconstruction of small molecules as a motivation for what we're going to discuss. Okay, so first of all, so cryo-EM is an inverse problem, and as every inverse problem, I need to tell you a bit about the image formation model, about the forward model. So So we have a molecule, okay, and let's say that phi is the electric potential or the scattering potential density. So it's just a function from R3 to R that we would like to reconstruct. And the data that we obtain are noisy tomographic projection images. So every projection image is obtained by basically integrating the density, say in the direction of the beaming electron, say in the z direction, after the molecule has been randomly rotated. Okay, so there is some element of the rotation group SO3, and you rotate phi, and then integrate in the z direction. So that would be a tomographic projection image. But on top of that, there is another, you can think of it as another convolution, or it's not just blurring kernel, but it's called the contrast transfer function of that comes from the microscope. I don't want to get into the details of the CTF, the contrast transfer function, but it is there, okay? And it could be different from one image to another. So the inverse problem, the basic reconstruction problem, is to estimate phi given n such noisy images. Okay, so that's the basic inverse problem in cryo-EM. And the heterogeneity problem that I mentioned before is not just to reconstruct a single phi, but actually to estimate the entire distribution of possible phis in the data, given the images. Now, it's probably going to be impossible to reconstruct individual, say, n individual structures, say phi 1 to phi n, because this will be a bit ill-posed, okay, going from n 2D images to n 3D structures. But if I just ask you to estimate the distribution of the phis, say if the distribution is low dimensional in some sense, say on a subspace, like say low dimensional in a subspace or in a low dimensional manifold, then this might be possible. So these are the two inverse problems that drive cryo-EM. As mathematicians, what we usually try to do is to say, oh, so this looks awfully familiar, this inverse problem, because in medical imaging, there is the classical CT, computerized tomography reconstruction problem, and it's a linear inverse problem if we know the rotations. So if we know the viewing directions, let's say if you want to do medical imaging and you have a patient that goes and undergoes MRI or CT, and so the patient is instructed not to move for the duration of the imaging process, because then the machine knows exactly the viewing directions. And then it's a linear inverse problem, and there are a lot of really mature numerical tools of dealing with. So as mathematicians, our first instance to say, okay, let's try first to estimate the rotations. And once we estimate the rotations, then we can solve the linear inverse problem and estimate phi. So that's the first instinct, and then you can say, okay, how am I going to estimate the rotation? So I told you before about the Fourier projection size theorem, and so this means that every two projection images, if we consider the 2D Fourier transforms, they are going to intersect at a line, okay, in the 3D reciprocal space, because every projection corresponds to a plane, so two planes will intersect at a line. This is known as the common line of intersection. This means that there should be one line in the second image and one line in the first image, where the values of the Fourier transform agree up to noise. We can probably find that line if there is not too much noise in the images, and then we can add a third image, and using say 3 images, we can find the relative orientations. This is called angular reconstitution. At the fourth image, fifth image, and so on, and even do it in a globally consistent manner. So so this is all great, okay, except for the fact that the identification of common lines is noise sensitive, okay. So as you as the signal to noise ratio goes down, they become less and less reliable. And over the year, we have developed better common line approaches that use semi-definite programming and synchronization of rotations. I will not discuss those today, okay? And on the other end, you can also try to improve the signal-to-noise ratio by doing some clever image denoising. So for example, if you have very large data sets, then images that correspond to similar viewing directions, if you can identify and rotationally align them and average them, then you can boost the SNR. Okay, so again, there are beautiful methods to do that using invariant representation of the images and using dimensionality reduction techniques like diffusion maps. And all of these, they certainly help, okay, to estimate the rotations of the images in a completely ab initio manner. However, what I would like to argue today is that estimation of rotations is impossible at very low SNR. So no matter how sophisticated we are as mathematicians, at very low SNR, it's going to be impossible to estimate the rotations accurately. And to convince you that that's the case, just consider an oracle that actually knows the 3D structure. Okay, so obviously we won't be able to do any better than an oracle that knows the 3D structure. And even an oracle would have a tough time estimating the rotation of very noisy 2D projections. Because what the oracle would do, the oracle would reproject the non-3D structure in all possible directions. And then for every noisy experimental image, the oracle would find the best match, the closest clean projection image among those that it used to reproject the molecule. But because the experimental images are so noisy, if you look at the correlation or the distances, they would fluctuate widely because of the noise. And the noise would just overwhelm the signal in the experimental images. So even the oracle would make very large errors in estimating the rotations at very low SNR. So you cannot expect like methods like SDP or synchronization to do any better than that. So this leads naturally to the following question. So if we cannot estimate the rotations reliably, does it mean that the structure cannot be estimated? Okay, or if we put it a more positive spin on it, can the molecular structure be determined at any SNR, even if rotations cannot be accurately estimated? Okay, so somehow to go directly and try to estimate phi without estimating the rotations, say R1 to Rn at all. Okay, so to completely bypass the estimation of rotations. So the method for estimating the 3D structure in cryo, the most popular method nowadays is based on maximum likelihood estimation, MLE. And I mean, this was proposed already in 98 by Sigworth and was really like implemented and perfected by Sheres and others. And for maximum likelihood estimations, they use expectation maximization, EM. It's very confusing, EM and cryo-EM, but hopefully whenever I say EM, you would not be confused about the context. So now EM refers to expectation maximization. And in this framework, you treat the rotations as latent variables, and which are marginalized over rather than being estimated. So in the EM iterations, there is an E step and an M step. In the E step, you do exactly what the oracle did before. Okay, so you have a current guess for how the 3D structure would look like. You project it in all possible directions. And now for every experimental image, instead of assigning the best match, you would assign a weight or a probability that it was actually taken from that direction. Okay, so now you do what is called a soft match rather than hard match. And in the end step, in the maximization step, you perform the weighted tomographic reconstruction. So basically you solve like the classical CT reconstruction problem, but now any given image can appear in many different directions. And you weight it according to the weight that you got from the E-step. So notice that in this framework, you treat the rotations as latent variables. So the parameter of interest in the statistical language is a 3D structure. And then you can actually still prove consistency of MLE. So you know that one of the really nice things about maximum likelihood that in the limit of increasing number of samples, when n goes to infinity, you should converge to the true parameter value. Notice that the number of rotations here grows indefinitely with the number of samples because there is one rotation per image. But if you just marginalize over the rotations and the only parameter that you try to estimate is the 3D structure, then you still have consistency. The issue is that EM, well, we know that may have problem, okay? It may converge to local optimum instead of the global one, where convergence may depend on the initial model. It could be very slow because you're going to need many iterations over the entire data set. So there are many heuristics and techniques that have been proposed over the years of how to accelerate that. From the mathematical point of view, it's a bit difficult to analyze, okay? So a very simple question of like, what is the sample complexity? How many noisy images do we need for successful reconstruction? We don't have a good answer for that by just looking at maximum likelihood. Okay, and that's something that we would like to understand. So in statistical estimation, like if you open any textbook on parameter estimation in statistics, the first two methods are the method of moments. Okay, so this was proposed by Pearson at the end of the 19th century, and which is really easy to compute if you can solve the moment equation associated with that. It is a consistent estimator, again, in the limits that number of samples go to infinity. It's even asymptotically normal, okay? So the error fluctuates like 1/square root of n, but it is not optimal, okay? So there are other estimators, like the MLEs that have a smaller variance error. There is maximum likelihood that I mentioned before. It is typically harder to compute. Okay, so in the case of cryo-EM, you need something like EM to try to find the solution, and it is not guaranteed that you would find it actually because it's a non-convex optimization problem, and all your guarantee is to find a local optimum. But it is optimal or efficient. Okay, it has the smallest variance among all possible estimators for large sample size. And if you can also incorporate some prior information, then this gets into the realm of Bayesian inference. So before we describe the method of moments for cryo-EM, let me just remind you of the method of moments, like for very simple problem of Gaussian mixture model in one dimension. That's actually the problem that Pearson did first. So here I show you, say, points on the x-axis, okay? Just sample from a mixture of two Gaussians. One is the red Gaussian and one is the blue Gaussian, okay? The blue here appears to the right of the red, so there is no political context here, okay? And you see the green is just the superposition of the mixture of the two distributions. So if I just show you data, and in the context of what I told you before, one way that you can go about is say, oh, let me try to cluster the data. Okay, maybe put, I don't know, here I see like a little well, I'll put my classifier here, everything to the left will be classified as red, everything to the right will be classified as blue. then you see that you're going to make mistakes, okay, in the classification. Okay, so the point that actually came from red are classified as blue and vice versa. And this is like, if you, even if you do it in the MLE framework, okay, that is consistent, because the number of parameters here that you try to estimate when you do clustering scales with the data size, and no consistency is guaranteed anymore, okay, only if the number of parameters is fixed. However, if you just try to estimate the 5 parameters of the mixture, okay, say the 2 means, the 2 variances, and the mixing proportion, then you're guaranteed of consistency. And the way that Pearson did it, he said, okay, let's start by computing the moments of the data, okay, the mean, the second order moment of the variance, the third order moment, fourth order moment, fifth order moment. Why 5? Because we have just 5 parameters to estimate. And then he solved the associated polynomial equation, but there was no unique solution. So you obtain finitely many solutions. And then you basically chose the one that best fits the 6th moment. Okay, so this was already done in the 19th century without computers. And okay. Alternatively, if you want to do macromolecular estimation, say using EM, then you would need multiple passes over the data until convergence, maybe. And in this case, definitely it's going to be slower than method of moments. Also, advantages of the method of moments here that you don't even need to store the entire data, okay? So all the computations can be done on the fly, like one data point at a time. You just update the moments. And then at the end of the day, you just solve the offline those 5 or 6 polynomial equations, independent of the size of the number of measurements. Okay, so now let's switch to the next moments for 3D reconstruction in cryo-EM. So I'm going to mimic that. Okay, so let's say that we have our n noisy 2D projection images of the 3D structure. The first moment will just be the sample average of those noisy images. The second order moment will be, okay, I'm taking an image and multiplying with itself at 2 different pixels. Okay, so now I'm going to get, you can see it either as a matrix or a 4D array if you wish, depending how you want to look at it. And in the third order moment, I'm going to multiply 3 different pixels. Could be same pixel, but okay, but potentially 3 different pixels, and then I'm going to get a 6D array. Effectively, these are actually one-dimensional lower because of in-plane rotational symmetry. So every image can appear in all possible in-plane rotations. So for example, the mean, okay, the average image, okay, is going to be radially symmetric. Okay, so it's going to be the same on concentric rings. Okay, it's going to be constant on concentric rings because you can just rotate every image, and this will be like a valid image of the data set. So it's 1D instead of 2 dimensions. Okay, the same goes here. Okay, the second order moment only depends on the 2 radii of the pixels and the angle between them. So it's effectively 3-dimensional, and similarly, this is going to be 5-dimensional. So now you ask yourself, okay, if the second order moment is 3-dimensional, does it contain enough information to estimate the 3D structure? Okay, because the number of parameters that we have is just about right. Okay, so certainly you will not be able to reconstruct from the first order moment, okay, from the average image. You lose too many parameters in the process. And it could be that the third order moment is needed, but you see it's much larger than what we need. Okay, it's 5-dimensional. So hopefully the second order moment is just what we need. Okay, so this takes us to the late 70s, early 80s, and there is a beautiful paper by Tzvi Kaum from the Weizmann Institute that considered exactly that problem, okay? when the viewing for the case where the viewing directions are uniformly distributed over the unit sphere. So there is no preferred orientation for the molecule. All orientations are just equally likely. And what Cam showed is that in this case, the second order moment is actually insufficient to determine the 3D structure. So let me try to show you quickly his argument. So basically what Cam argues is that the second order moment is equivalent to computing the autocorrelation function of the Fourier transform 3D structure with itself over the rotation group SO3. And why this is the case, again, because of the Fourier projection slice theorem. So if you consider the second order moment, but now let's say in Fourier space instead of real space, okay, so suppose that here I have the Fourier transform, and now I multiply two values of the Fourier transform of an image with itself, okay? Then we know that because of the slice theorem, these are actually equivalently, I could have multiplied the values of the 3D Fourier transform of the molecule with itself because of the slice theorem. And now when I do the summation over all images, then basically every image gives me a different slice. But all slices are equivalent by just rotating over SO3. So this sum, you can think of it as basically as a Monte Carlo integral, okay? As a way to compute an integral in a Monte Carlo fashion. And the order of the summation doesn't matter. So every time I take some, so this is basically what we are computing here is an approximation to the integral over SO3 of the Fourier transform of the molecule times itself, okay, which is nothing but the autocorrelation of the molecule with itself over SO3. Okay, so that's what Cam showed. Okay, I'm sending you the derivation. Basically, I just told you in words how it goes. Now we know that if I give you the autocorrelation function of a signal, it's usually insufficient to uniquely determine the signal. For example, in one dimension, if I over the line, if I give you the autocorrelation, if I give you the power spectrum of the signal, then you would end up with the notoriously famous phase retrieval problem. Okay, and so the signal is going to be unique only up to those missing phases. And similarly, this is what happens in cryo-EM. If phi hat is a 3D Fourier transform of the molecule, and I expand it in spherical harmonics, okay? So YLMs are the spherical harmonics, and the ALMs are a function of the radial frequency, but these are unknown coefficients, okay? Or unknown functions, if you wish, of the radial frequency. Then from the second order moment, what you get are matrices called CL. And so these are, you can compute those from the data, but the way they are related to the unknown coefficients is by this equation, okay? So CL at K1, K2 is the sum over M from minus L to L, okay? So this is the M in the spherical harmonic expansion. So there are 2L plus 1 of these. ALM K1, ALM complex conjugate of K2. Or in matrix notation, I can write CL as AL complex conjugate transpose. So this means that the ALs are determined only up to a unitary matrix. And if you also include the fact that the molecule is real valued, then it's actually only up to an orthogonal matrix. So for every L in the spherical harmonic expansion of the molecule, we can determine the ALs, the coefficients, but only up to a missing orthogonal matrix. So for L equals to say 1, we're missing a 3 by 3 matrix. For L equals to 2, we're missing a 5 by 5 matrix, and so on. Which is very nice because we don't have the dependency on the discretization in the k direction. Okay, so it's a 3, 5, 7, and so on, but we're still missing those matrices. So the structure is not determined uniquely from the second order moment. Now, for those of you who worked on the phase retrieval problem, okay, and I know that in the audience there are at least some of you who've looked at phase retrieval very carefully, I would just say there are lots of interesting connections between the missing phase problem in X-ray crystallography and the missing phase problem that comes from Kamm's method. And okay, so first I'll tell you what else we know in the case of uniform viewing angle distribution beyond the work of Kamm. So, okay, so we know that second order moment is insufficient. Now, Kamm already in his paper, he proposed using higher order moments, like third order moment and even fourth order moment, to help with the uniqueness issue. And at least empirically, he observed uniqueness. There is a bit of,
Amit, sorry. So is there actually a mathematical proof of that the third order moment is mathematically sufficient to recover?
So that's exactly the next sentence that I was about to say.
Well, that's it. That's only for the regular representation. Did they do it for SO3 also? For
yeah.
SO3? Okay, so they did do that, right?
Yeah. So yeah, so that's in that paper on the ICAR by Afonso and others, and then what can also be shown that this is actually information theoretical optimal. Okay, you cannot do any better than that. Now, okay, on the other end, we know that at ISNR the story is different. Okay, at ISNR the number of samples that you would need is proportional to 1 over the SNR, not 1 over SNRQ, because then you can actually estimate common lines and do averaging or synchronization, and the story is very different. Still, this is a bit unpleasant, okay, to use third order moments, because first of all, I mean, they are much more difficult to use in practice, in the sense that, well, to estimate accurately the third order moment, you would need many more images, as sigma to the 6 instead of sigma to the 4. The third order moment has much higher dimensionality, okay, like I told you before, it's 5-dimensional instead of 3-dimensional. And in terms of statistical estimation, at least I'm not aware of like existing eigenvalue shrinkage procedures like we have for high dimensional covariance estimation in the tensor case. So the question is, can we somehow avoid the third order moment and still stick with the second order moments? So there are at least 2 ways of avoiding third order moments and still working with second order moments. One is if instead of a uniform distribution of viewing angles, we have a non-uniform distribution of viewing angles. And that's actually the more practical case, because in practice, usually molecules have some bias in the distribution of rotations. Okay, it doesn't have to be like a very preferred orientation, but sometimes there are some preferred orientations. And I mean, often distribution is not completely uniform. And in those cases, we can actually show that the second order moment is sufficient to determine the 3D structure, which is a bit of surprising, at least at first. Well, at least for those who are not too familiar with multi-reference alignment, but it seems like the cryo-EM problem should be more difficult when the distribution of rotation is not uniform, because the coverage in the 3D Fourier space is now less optimal. But it turns out that from the point of view of not knowing the rotations, this is actually a better situation. And somehow it breaks the symmetry that we have when we just try to do, say, in Kamm's method with the uniform distribution of viewing directions. So then the procedure would be very simple. Like I would give you 2D images. All I need to do is somehow to do PCA, to commute the covariance matrix, And then from the covariance matrix, you should be able to compute the 3D structure. Now that would be like a dream come true. Right now, we cannot actually fulfill this dream because the method is limited to only to low resolution. So we can determine structure only at low resolution. It's unclear where is if the difficulty is some computational hardness or what is actually preventing us from going to higher resolution. Another avenue to bypass the need for third order moments is sparsity. So to assume that the molecule has a sparse representation in some basis, for example, like a wavelet basis, or I think Dustin asked me before the talk about the Wilson model. So that the molecule is really made out of is a superposition just of just atoms. Okay, so a superposition of ideal point masses. So and whose only just their locations are unknown. So in those cases we can actually, well, at least in the case of point masses, we have a result that says that yeah, the second order moment is sufficient. So this is in this paper is in final stages of preparation. And in the case of say the molecule sparse in a wavelet basis, we're very encouraging numerical results that second order moment suffices. But still, these are again limited to low resolution. So we cannot somehow break the resolution barrier. So it may suggest that there is some fundamental limitation here that we don't fully understand. And this is also related to the point of sparse multi-reference alignment. I'm not going to go into it, but for those familiar with phase retrieval, so you can say how to solve phase retrieval when you know that the underlying signal is sparse in some basis. Okay, so in the very limited time that I have left, I'm not going to finish all my slides, but I'll just briefly mention the final topic that I want to say is how to do cryo reconstruction for molecules that are just too small to be even detected in the micrographs. So these are situations that just like we cannot assign rotations to the images, we cannot even localize the images in the particle images in the micrograph. So this is just that small molecules are very hard to see, okay, and detect. So you can realize why it's more difficult to reconstruct small molecules in cryo-EM. So let me just illustrate the problem, okay? So before doing like the full cryo-EM problem, if I show you the micrograph on the right, okay, and you just tell me, Amit, it's just white noise, but if I tell you, no, there is actually an image that to be reconstructed here, and that image appears many times in this micrograph and many other micrographs that I collected, then because there is a repetitive signal, there might be a hope of recovering it. Okay, so if in the clean case, it's very easy, okay? Just pick one of the instances of the image of Einstein and you can estimate. Even in the noisy case, you say, okay, it's very easy to do particle picking, do the image segmentation, find the location, and then average the instances, and we'll get a really good image of Einstein. But what to do if you cannot even find Einstein in the images? Okay. So the idea is again to use the method of moments or autocorrelation analysis. And so, for example, the first order moment here would just be the average pixel value. So the average pixel value would be the average pixel value of Einstein plus the average pixel value of noise. The average pixel value of noise would be 0. It will cancel out and we'll get some information about Einstein image, okay? Very little information. And then we can go to second order correlation. So I'll take 2 pixels, okay, multiply their value and average over the entire micrograph. And every time I'll do it with some different displacement. So I'll get the autocorrelation function. And the nice thing about this autocorrelation function is that they are invariant to the specific locations of where the images are embedded in the micrograph. So the autocorrelation would be the autocorrelation of the Einstein image with itself, plus the autocorrelation of the noise with itself, with, let's say that we know it's white Gaussian noise, so we know what's the power spectrum, and the autocorrelation of Einstein with noise that would average out. So here I'm assuming some technical assumptions that the images are sufficiently separated from one another, that there is no interaction between that image of Einstein and that image. Okay, and even that technical assumption can be relaxed. So from those autocorrelations, then you can solve, say, a phase retrieval problem and get a really nice reconstruction, okay, with an increasing number of micrographs. So this shows that you can estimate the image without doing detection, okay? So you can do estimation without detection, and this method of moments, or autocorrelation, as in this case, is a very powerful and efficient tool to this end. But then you can tell me, oh, but I mean, this is not real cryo-EM. I mean, you took a single image and just place it in different locations. Okay, so let's do one level of difficulty higher. Let's say now the same image, but now arbitrarily rotated. Okay, so here is an image of a very low-res image of a tiger, and now placed at different location, but also arbitrary in-plane rotated. And again, we do first order, second order, and here also third order autocorrelation, because second order autocorrelation would be insufficient. And from those first three autocorrelation function, we can estimate back the image. Okay, so this also works. But again, this is not cryo-EM, okay? So to see how many correlations we need for cryo-EM, so here are the autocorrelation functions. And you can see the third order autocorrelation, okay? Again, it is a 4-dimensional array, okay? So tau1 and tau2 are some displacement. But because of in-plane rotation in advance, it will be 3-dimensional. So here the third order autocorrelation will be 3-dimensional, and if we are lucky, then it means that from this triple correlation function, or the bispectrum of the images, we should be able to reconstruct the 3D structure. And so in 1D it works very nicely, okay? So this is in 1D, and there are comparisons here that I show between autocorrelation analysis and EM. So you see that the error is more or less the same. And here is the very nice story that the slope here is 3, meaning that at high noise variance or low SNR, you really need number of samples that scale like 1 over SNR cubed. At high SNR, you need number of samples that scale like 1 over SNR. There is a clear advantage in terms of running time to autocorrelation analysis over EM. You see that at some point the SNR gets so bad that the number of iteration EM needs starts rising, okay? And this is bad news for the running time of EM, whereas the running time for autocorrelation analysis always remains the same. Just one pass over the data and one time solution of the moment equations. So let's see now if somehow in cryo-EM this works, and the answer is very similar to the case of the second order momentum and non-uniform distribution of rotation in Kamm's method, that it works, but not perfectly so. Okay, so here are 2 instances of 2 different molecules. These are the ground truths that you see in purple. These are clean micrographs that you can generate from them. These are noisy micrographs, not at the level of noise that you'll be unable to see the molecule, just so you can actually still see the molecules, and believe me that we're doing experiments with noisy data. This is just a low pass filter of the ground truth, okay, to the resolution that we can actually reconstruct. Okay, so this is the reconstruction from clean micrographs, and this is the reconstruction from the noisy micrographs. And you can see that at low resolution, we're doing a good job, but again, we're still unable to push this method to high resolution. And again, it's not completely clear why. So let me just summarize at this point. So autocorrelation analysis was proposed by Tzvi Kamm at late 70s, early 80s for peak particles with uniform distribution of V directions. And we extend CAM theory in 3 important ways. One is to allow for non-uniform distributions. The other is to incorporate sparsity. And the third is for the case when particles cannot even be picked from the micrograph, cannot be detected. We bypass completely orientation estimation, alignment, and particle picking. The advantage of autocorrelation is that they can compute it by just one pass over the data in completely on-the-fly manner. And despite widespread belief, there is no theoretical small size threshold for reconstruction by a single particle cryo-EM. So at least theoretically speaking, if you need a low resolution reconstruction, you can do it for arbitrarily small molecules that cannot even be detected in the micrograph. Now for the mathematicians in the audience, I didn't go into the technical ingredients of how we prove things and how we show that the algorithms work and things like that. I just want to mention that the methodology that we use combine tools from Fourier transform, Fourier analysis, statistics and machine learning, numerical analysis, dimensionality reduction, optimization, algebra, and information theory. So it's really a combination of widespread fields. And if you like any of those, then I really encourage you to look into cryo more seriously. So thank you very much for listening.
All right, let's thank the speaker, smash that reaction button.